Okay, in this lab, we're going to look at the motion of falling bodies. That is, objects that are falling because of the Earth's gravity pulling them down to the ground. Now, we can begin our investigation of motion by reminding ourselves of Newton's laws of motion, which are sort of the laws that Isaac Newton came up with, which explain how motion works in the world. Now we can talk about Newton's first law of motion. This is Newton's first law of motion, and I'm going to state it in a very simple way. But first, let's talk about what Newton's first law of motion is. It's a law that relates acceleration to force. That is, if I have a given force acting on a body and I cause that body to accelerate, what's the relationship between the force and the acceleration? And in order to talk about that, we need to understand what an acceleration is. Now, in the last module, we talked about acceleration as being a change in velocity divided by a change in time. So it's the rate at which velocity is changing. And when we talk about what it means to change velocity, remember it means we can do it in one of three ways. We can speed it up, we can slow it down, that is, either of those represent changing the speed. We can change how fast the object is going by speeding it up or slowing it down. Or since velocity is a vector, remember vectors have a direction, we can make it turn. We can change its direction. So any of those three things, speeding up, slowing down, or turning, represents an acceleration. And in order to get an acceleration, you have to apply a force. That's what Newton's first law tells us. Now, just to be clear, the units of acceleration are meters per second, meters per second every second. That means the velocity is changing 5 meters per second every second. That's going to be 5 meters per second. It's kind of a weird thing to say, and that's meters per second squared. And oops, that should be s to the second power there. My PowerPoint screwed up, but anyway, we'll just go with that. So that's what an acceleration is. Remember, it's speeding up, slowing down, or turning. And we're going to relate that to force, which we can think of as simply a push or a pull. And the units of force are going to be either the pound or the Newton, named, of course, after Isaac Newton. The pound is the unit of force that we normally deal with in the English system of units. The Newton is the unit of force in the metric system of units. And by the way, a lot of people don't really know how much a Newton is. I mean, if I told you something is 10 pounds, you'd kind of have a sense of what that means. 10 newtons, most people don't know what that means. Well, if you ever encounter newtons, just think of an apple. Remember the story of an apple fell on Newton's head and he discovered gravity? Well, an apple weighs about a newton. Incidentally, one of the original iPhones, another kind of apple, that also weighs about a newton. So it's kind of a funny coincidence. But in any case, that gets us what an acceleration is, that gets us what a force is, and now we can note that Newton's first law says very simply, to accelerate an object, you must apply a net force. And you'll see it written in many different ways, many more complicated ways. Your textbook writes it in a more complicated way, but I think this is the simplest way to state it. To accelerate an object, you must apply a net force. So that suggests the question, what is a net force? Well, a net force simply means the total amount of force that you have acting on an object. And remember, force is a vector, so again, the direction matters. So if I look at this box here that's being acted on by two different forces, I have a 3-pound force pushing to the right and a 6-pound force pushing to the left. Well, the 6-pound force is going to win. And the box is going to move to the left, it's going to accelerate to the left, as if there were a single 3-pound force acting on it. So here I've written in, there's sort of a net force of 3 pounds here, and it would be a net force of 3 pounds to the left. 3 pounds to the left. And that's important because, again, all these things we're talking about, force, velocity, acceleration, these are all vectors, so the direction is very important. Now we're going to move on and talk about Newton's second law. Now, the first law that we just covered, it tells us that to accelerate an object, you have to apply a force. The second law tells us how much acceleration a given force will give you. And it depends on the force and the mass. So those are the two things that the acceleration depends on. And this is Newton's second law. The acceleration is equal to the force divided by the mass, or you could do some algebra and rearrange that, and you would get that the force is equal to the mass times the acceleration. This is the way that it's actually usually written, F equals m times a. But in terms of the definition, this is kind of a better definition. The acceleration is the force or the mass, because that relates it better to the first law. Now, we know that force is a push or pull. Mass, you guys all know that mass is essentially how much stuff an object has. I mean, you could almost think of it literally as counting protons and neutrons. You know, if I have a block of gold that's got twice as big, it's got twice as many protons and neutrons all in it, that's going to be a block that has twice the mass. So we could talk about a 1 kilogram block of gold or a 2 kilogram block of gold. So the bigger the mass, the more stuff you have, the bigger the force or the smaller a force. Those are the things that are going to impact the acceleration. And what this equation tells us is actually pretty simple. It just tells us that a bigger force is going to give a bigger acceleration, and a bigger mass is going to give a smaller acceleration. Why is that? Well, if I've got a bigger force, I'm multiplying by a bigger number, so I get a bigger number in my answer here. And if I have a bigger mass, I'm dividing by a bigger number. So that's going to make the acceleration smaller. Now we can talk about this in terms of the force of gravity. So the acceleration due to the force of gravity, or simply the acceleration due to gravity, it turns out is something that's constant. And so if you're near the surface of the Earth, the force of gravity is basically constant. And since force and acceleration are related to each other by F equals ma, the acceleration is also going to be constant near the surface of the Earth. And in fact, there's actually a value. The acceleration due to gravity has a value of 9.8, and this 2 here should be a superscript again, so that should be meters per second squared as the units. So the acceleration due to gravity has a value of 9.8 meters per second squared downward. What does that mean? Again, that's telling you how rapidly the velocity of an object is falling. The velocity of an object is changing as it falls. So if we drop an object, if we just hold an object above a tall cliff and we let it go so that it falls, after 1 second, it's going to have a velocity of 9.8 meters per second, because the amount of velocity change is 9.8 meters per second every second. So after 1 second, it's going to have a velocity of 9.8 meters per second. After 2 seconds, it's going to have a velocity of 2 times 9.8. After 3 seconds, it's going to have a velocity of 3 times 9.8. Every second that that object falls, its acceleration causes the velocity to increase by 9.8 meters per second. And so that tells you how things speed up as they're falling. And this is not obvious, but gravity causes all objects near the surface of the Earth to accelerate at the same rate. And people didn't used to realize this. In fact, Aristotle, who was a very famous scientist and philosopher, he actually got it wrong, and he said that heavier objects would fall faster than lighter objects. And, you know, you might think of that. It makes sense in a certain sense. If you lift a heavy object, you might think that if you dropped it, it would fall faster than a lighter object. But it turns out not to be true, because that bigger object also has a bigger mass. And that means for a given force, the force of gravity, the acceleration gets lower. And so it cancels it out. The force of gravity is higher on a bigger object, but the acceleration goes up because of the force of gravity, but the acceleration also goes down because of the bigger mass. And so it equals out so that all things near the surface of the Earth accelerate at the same rate. And we can see this with projectile motion. Now here's a picture of another very famous physics experiment where you have two objects, and one of them is released and it falls straight down, and the other one at the same time it's given a little kick, say off the edge of a table or something, and so it falls down as well, but it's also got some motion to the side. And if you look at this each spot represents sort of a picture of the object after a particular time interval, say a third of a second or something like that. So at this time they're released together. The green one is launched to the side, the purple one is going straight down. After one time interval, both fallen the same amount. After the second time interval, they've both fallen the same amount. After the next time interval, again, they've both fallen the same amount. All objects near the surface of the Earth fall at the same acceleration. Now, that is, of course, ignoring air resistance. We are ignoring air resistance, and sometimes air resistance is important. But in a lot of situations, the effect of air resistance is essentially negligible, so we don't have to worry about it. But if the air resistance is big enough to create an effect, then gravity is not the only force, and the net force would change. And so if gravity is the only force that we have to worry about, that is the net force, and it'll give you the acceleration of 9.8. If there are other forces acting on an object, then the acceleration can be different because the net force changes. But again, that's not really something that you really want to worry about too much. But these are the things that we're going to investigate in this week's lab. We're going to look at falling objects, and we're going to see, is it true that all objects fall at the same rate, regardless of how much mass they have? And also we're going to look at the possibility that maybe air resistance can sometimes change that and create an impact. And so that's the end of this presentation. So you guys can go on and read through the course document on this experiment, which will give you the experimental procedure. And I have a video linked showing you an experiment showing how that, when you remove air resistance, all things actually do fall at that same rate. But that's going to be something that you can test yourself. So good luck, and so go through the experiment. When you finish the experiment, you'll be ready to take the quiz.